Good morning. Here we are going to start Fundamental Theorem of Algebra. Before starting this, we are having some remarks which are helpful to prove this theorem. The first one is, an entire function that is not a polynomial is said to be a transcendental entire function. Now, what is a transcendental function? The function which is not algebraic. That is a transcendental function. Second one is, every continuous function on a compact set is bounded. And if you are having a compact set, then it must have two properties, that is, it should be closed and bounded. So the set which is closed and bounded can be taken as your compact set. Now the theorem, Fundamental Theorem of Algebra, which states that every non-constant polynomial has at least one zero. At least one zero means it has at least one root. So suppose we are taking a polynomial which is non-constant. So let's start with the proof. Suppose Pz be your polynomial. I'm taking Pz to be equal to a0, which is a constant, a1z. a1 is a coefficient of z, plus a2z square, plus so on, an zn. Now this polynomial to be taken as non-constant, we should have an to be non-zero, right? What we have to prove that it has at least one zero, that means it has at least one root for which one value for which this pz vanishes, right? What is the meaning of root? That means suppose you are having a function to be as x minus 1. What is the root for this function? X equal to 1, for which, at the value for which this function vanishes, right? So we have to prove that this polynomial has at least one zero, at least one root. So we do this result, we do prove this theorem by a contradiction. So we have to suppose the other way. Suppose pz never vanishes, or it has no root, right? So if possible, suppose pz never vanishes. That means we can define 1 by pz, right? Then 1 over pz is defined, because if pz is 0, then 1 over pz cannot be defined. This will be infinity, right? So pz never vanishes means 1 over pz can be defined, and it is an entire function. Why? Because pz is given to be your entire function. So 1 over pz is also an entire function, since every polynomial is an entire function, right? So if pz is entire function, then 1 over pz is also entire function. Entire function means analytic everywhere. So therefore, can I write 1 over pz, this tends to 0 when this 1 over pz tends to 0? If as z tends to infinity. What is pz? a0 plus a1z plus a2z square. If z tends to infinity, then pz tends to infinity. If pz tends to infinity, then 1 over infinity tends to 0. So 1 over pz tends to 0 as z tends to infinity, right? So thus can we take epsilon, a positive epsilon, for Thus for epsilon positive, there exists a positive real number. Let us suppose that R, such that 1 over pz, this mod is less than, this is less than epsilon for mod z greater than equal to R. See, z is tending to infinity. That means if we create a circle, take this your positive real number to be R. Now for if z is tending to infinity, that means if I take outside the circle, this 1 over pz is bounded by epsilon, right? So outside this circle the function is bounded. This is your mod z greater than equal to R. And inside the circle, this is your mod z less than equal to R, right? Now if I take epsilon to be equal to 1, I will be taking epsilon to be a positive 1. Let's take epsilon to be equal to 1. So thus for epsilon equal to 1, there exists a positive real number R such that 1 over pz mod is less than 1, because it is tending to 0. So can I write this mod to be less than 1? Yes, for mod z greater than equal to R, right? Now this mod less than 1 implies its boundedness, right? So let's write therefore 1 over pz is bounded for mod of z greater than equal to R. Now what about mod of z less than equal to R? Is the function bounded or not? Is 1 over pz bounded or not? See, we are having one result since pz is your entire function, right? So pz, 1 over pz is also entire function. An entire function is a continuous one. So your 1 over pz is continuous. Right? And we have just read in remark that every continuous function is bounded on the compact set. And if you look at this, mod of z less than equal to R, is this your compact set? Yes. First one, mod z less than R, implies its boundedness. And mod of z less than equal to R means it is closed set. If mod of z is strictly less than R, then this is bounded and open set, right? Whenever you give your equality sign here, the set becomes closed. That means all limit points belongs to the set. Here if it is strictly less than R, that means it is an open set and limit points need not belong to the set. And if it is closed, we write equality sign with less than. So this means all the limit points belong to the set and it is your closed set. Similar is the case for the intervals. If you are having open interval, this is your open interval. And if A and B includes in the set, then we give this sign. This is your closed interval, right? So here A and B are the limit points which belongs to this closed interval AB. Similar is the case for the circle. So mod z less than equal to R means you are having a circle which is bounded and all the limit points also belongs to the circle, right? So mod z less than equal to R is compact set, which is bounded and closed. this mod z less than equal to r, this is your compact set, and every continuous function on the compact set is bounded. So your 1 over pz is bounded outside as well as bounded inside. That means it is bounded for mod z greater than equal to r and also bounded for mod z less than equal to r. This implies 1 over pz is bounded in the whole plane, right? So let's write that. Since it is continuous and we know that every continuous function on the compact set is bounded. So 1 over pz is bounded on the compact set. What is that compact set? Mod of z less than equal to r, right? So thus from 1 and 2, this is your 1 and this is your 2. It is bounded for both the conditions. So from 1 and 2, 1 over pz is bounded in the whole plane, right? Yes. Now this 1 over pz is your entire function and now it is bounded also. So this becomes bounded entire function. Entire function तो था ही, but अब साथ में ये bounded भी हो गया है. So what the Leibniz theorem states that bounded entire function must be a constant. So if 1 over pz will be your constant by Leibniz theorem, that means pz is constant, but in the theorem it is given that your polynomial should be non-constant. So here the contradiction comes. I'm right only L by Leibniz theorem. One over pz is constant and hence pz is also constant, which is a contradiction. That means our supposition was wrong. What is our supposition? That pz never vanishes. So this supposition was wrong. It should vanish for at least one point. Thus, pz vanishes at least for one value of z. So hence pz vanishes, pz has at least one zero. This only we need to prove? Yes. It has at least one zero. Sorry. Right here proof ends up. Now some of the corollaries for this theorem. Let's do that. Similar proof, nothing different. So first corollary is every polynomial of degree n has exactly n zeros. Just now we have talked about that this polynomial has at least one zero. But if your polynomial is of degree n, then it has exactly n zeros, right? So proof will be the same. Let's see that. Suppose again you are having pz to be your polynomial like this of degree n. We have to take an to be non-zero. And again we suppose that pz never vanishes. 1 over pz is entire function, tends to 0 as z tends to infinity, the same proof. Again we get that outside the circle and inside the circle 1 over pz is bounded, and by Leibniz theorem this will be your constant. Pz is your constant, which is a contradiction. So our presupposition was wrong. It vanishes at least for one value. Now say that one value to be equal to R1, say. Then what is your polynomial function? Your PZ will be Z minus R1 QZ. Now this polynomial will be of degree n minus 1 because one root vanishes, right? Your PZ is of degree n. One root vanishes. Suppose it gets its root as R1. The P of R1 is 0, right? So now its degree will be less than n by 1. So its degree will be n minus 1 because one root vanishes now. If two roots vanishes, then its degree will be n minus 2, right? So now PZ can be written as Z minus R1 QZ, where QZ is a polynomial of degree n minus 1. Now repeating the above arguments, we can show that now you take this QZ to be same as what we have taken for the PZ. Take this polynomial with degree n minus 1, start the same proof, and you will get that this QZ is now having at least one root, say that is R2, right? And now QZ will be of the polynomial with degree n minus 2. You take then another LZ, right? So going like this process can be repeated n times to obtain n zeros of the polynomial PZ. First 0 R1, then second 0 R2, then again we repeat the steps, then we get R3. Going like this, we get our n roots, right? Hence, every polynomial of degree n has exactly n zeros, not necessarily distinct, right? The other corollary, every polynomial of degree n assumes each complex number exactly n times. So now the result, we have to prove that this polynomial which is of degree n that assumes each complex number n times. This is also just the same proof. Let's write. Suppose we take our PZ to be a polynomial of degree n. Let PZ be a polynomial of degree n, right? And we have to take any complex number, and suppose that let A be any complex number, right? Then we'd suppose our QZ to be equal to, let's say, this PZ minus A. Since if I skip or if I subtract a complex number from a polynomial, then degree remains the same, right? If suppose you are having a polynomial 2x squared plus 3, if you subtract some complex number from here, then degree remains the same. Suppose your complex number to be equal to 1 plus 0 iota, then degree will remain the same, right? Only constant they will simplified, but degree remains the same. So if you subtract any complex number from a polynomial, then degree of QZ remains the same. Now what we have, this is also a polynomial of degree n. This QZ is also a polynomial of degree n. Right? What we have to prove that this QZ has n zeros. First we have to prove just like the before corollary 1, we proved that the polynomial has exactly n zeros. We have to prove that this QZ has n zeros. We have to prove this. So now the same result is going to be done, same proof is going to be done. So let's check the proof for this. Now suppose you have to take that QZ never vanishes. Again, suppose likewise just as PZ, suppose QZ never vanishes. Alright. Then 1 over QZ is your entire function. then therefore 1 over qz tends to 0 as z tends to infinity. Repeating the same steps, just replacing pz by qz. Just repeat the same steps. Alright, and we get at last we get the result. Hence qz has, suppose, at least 1 0, say r1, say, right? So now qz can be written as z minus r1. We take now another, let's say lz, another function, let's say lz. So where lz will be the polynomial of degree, qz is a polynomial of degree n, so lz will be a polynomial of degree n minus 1. Right? So now repeating the again same arguments, we can show that this lz has at least 1 0, say r2, right? So repeating above arguments or above steps, we can show that lz has at least 1 0 r2, say, right? So this process can be repeated n times to obtain n zeros of the polynomial qz. So this process likewise can be repeated n times to obtain n zeros of the polynomial qz. So now qz has exactly n zeros. So qz has exactly n zeros. And what are those zeros? r1, r2, r3, so on up to rn. These we are getting the zeros of qz. But what is our qz? Qz is equal to pz minus a, right? So if qz has r1 root, then q of r1 is equal to 0, and from that we can get p of r1 minus a is equal to 0, right? Similarly, if r2 is a root, then q r2 is equal to 0 means p of r2 minus a is equal to 0. So for r1, r2, r3 we are getting p r's 1, 2, 3, whatever it is, minus a equal to 0. We are getting the same value. So can I write from these two that p of r1 minus a is equal to p of r2 minus a, up to so on, p of r3 minus a, all these are equal. So I take this 1, 2 as j. Okay, I select a variable for them. So I write p of rj, say, minus a is equal to, what is p of rj minus a? It is q of rj, right? Which is equal to 0 because rj is a root of qz for all j equal to 1, 2, 3 up to n, right? which implies P of Rj minus A is equal to 0 for all j from 1 to up to n, which implies P of Rj is equal to A for all j 1 to up to n. That means P of R1 is equal to P of R2 is equal to P of R3 up to so on equal to P of Rn is equal to A. All these values for R1, R2, R3, Rn is equal to A. What does this mean? This polynomial Pz, it is assuming A as n times, right? So Pz assumes A exactly n times, right? Because we are getting for R1 to be equal to A, for R2 this value is A, for R3 this value is A up to so on. So this is assuming A exactly n times, but your A was arbitrary. A is any complex number. So but A was arbitrary. So now can I write the result for each complex number? It is assuming each complex number exactly n times. So hence every polynomial of degree n assumes each complex number exactly n times, right? So we now see how the behavior of an analytic function at a sequence of points influences in behavior elsewhere. So this ends up with the proof. Next time we will be doing your maximum modulus principle and minimum modulus theorem. Schwarz-Lammer has already done. You can check those YouTube videos of mine. So if you are interested in getting my course Real Analysis, you can check the description box. The link is given for that course. You can have that. So thank you for watching this video. Have a good day.